Let's resume the second part of the lecture. We have one more thing to say about directed resolution. And this is the role it can play in constructing what we would call a decision tree that captures the models of the underlying CNF. So we're looking at this example here. We have this particular knowledge base. And what I drew here is what we would refer to as a decision tree. This is a concept that you've been exposed to probably in other contexts, typically when talking about classifiers. But the decision tree is a more general concept that can be used in this case to characterize the models of the knowledge base, that is, those variable instantiations that satisfy the knowledge base. What you see here is nodes that correspond to variables, and then every node has two children, which we call the high child and the low child. And the idea is high child correspond to setting A to true, and the low child is setting that variable to false. And if we want to read this, we'll see that it can be used. If you give me a variable instantiation and you say, does that satisfy the formula or not, then we can use the decision tree to decide. But let's just keep going with this. So I have these guys, and then at the very end, there is either false or true. These are the leaf nodes in the decision tree. You can think of these as signifying whether a particular instantiation satisfies the formula or not. So let's take an example. If you have a variable instantiation, let's say that corresponds to A equals true, B equals false, C equals false, D equals true, and E equals true, right? And then you tell me, does this satisfy that particular guy? Well, we start at the top and see what is A is. A is true. We go this way, false. Already know. I don't have to check the others. This does not satisfy the formula, right? So let's make it a little bit different. So let's say this is A equals false and keep everything else. So then you would start here and A false, you go down the low child. B false, I'll go here. C false, I'll go here. Now what happened? I got true. So look what happened. Actually, let me spell this out. So B equals false, C equals false, D equals true, and E equals true. What happened is the minute I checked these three guys, that is A false, B false, C false, I got true. That means this will satisfy, and it doesn't matter what these guys are. I didn't need to check them. In this case, they're true and true, that's fine, but they could have been anything else. So the minute you set A to this, B to this, and C to that, you know that you have satisfied the formula and you don't have to worry about anything else, okay? This is a decision tree. In a sense, if you look at the decision tree, you can think of it as enumerating the models of the Boolean formula. In particular, if you go and trace from the root to those nodes that are true, those actually characterize the models of the formula. So, and in fact, by looking at these true variables or true leaves, you can even do something else, which you're going to tell me, try to guess. What else can I do beyond just enumerating? So there is a question about how did we make this tree? We're going to get to this. And what can you do with these true nodes? Can you tell me one thing else we can get out of this tree? So it gives me an efficient way to check whether something is a model, but what else? If you go down this path, right? So A false, B false, C false, the fact that I didn't have to test these two guys tell you that there are 4 different ways in which you can complete this and get a model. So if you look at this node here, it's actually characterizing 4 different models for this particular knowledge base, right? So A false, B false, C false, and D and E could be anything. So this is already characterizing 4 different models. Let's look at the other guy here. So if we go down here, how many models does this guy characterize, this leaf node? So this is A false, B false, C true, D false, E. Okay, just one. Let's see, where else do we have true? We have this guy here. If we go down here, how many models is this characterizing? This guy. So we fixed A, we fixed B, we fixed C, we fixed D, and E is still free. 2 of them, exactly, because E could be anything. Now, all of the other guys are false. And what happened here is that if you look at these 4 models and this one model here, are they distinct? Are they distinct? Do they overlap, the 4 models here and this model here, right? Because of the way this is constructed, look at C. Everything here has C false, and everything down there has C equals true. So they're actually disjoint. Similarly for this. So the 2 and 1 and 4 are distinct, which means if I want to count the models of that are characterized by this decision tree, I can just add 4 plus 1 plus 2 equals 7. And I have 7 models for this guy. Okay, so effectively, when you have the decision tree, it's like you enumerated the models or have a way to easily enumerate the models of the knowledge base. And you also have a count of the models of the knowledge base. Now, 2 things I want to mention about this decision tree, which are, you know, in general is not necessary. We have an ordering. So if you go from the top to the bottom, the variables are always A, B, C, D, E. In general, in a decision tree, they don't have to be ordered. But the reason we have them ordered here is for a particular reason that we're going to mention next. And realize we're also avoiding nodes where you would have like a variable X and both guys are true. That doesn't make sense here. We can just have a true there. And similarly, if you have a variable X and you have the children both as false, we're not doing that. We can just have a false there. Okay, because this basically means that this variable is irrelevant from that point of view. Okay, now we have this. Someone is asking about the 7. The 7 is we added 4, 1, and 2. The point is, how do you construct something like this? One way to construct this is, let me erase something here. The question is, how do you construct it and construct it relatively efficiently? By efficiently mean I don't want to do more work than effectively the size of this tree. If you have access to a consistency test, that is where you can check the consistency of a knowledge base with some variable setting. Then you can do the following. You can say, okay, let me go and start with A, and let me start with A, and let me go and say, okay, let's say A is true. What happens in that case? Well, you can go and add A is true to your knowledge base and check whether that is consistent. If it is not consistent, which is what the situation here is, if you take A and add it to the knowledge base and check this not consistent, you put a false and you're done. And then you go and say, let me check that A is false. So what does that mean? You go and add the clause not A to the knowledge base and check whether that's consistent or not. In this case, you will find that actually this is consistent with the knowledge base, which means that now for B, you can go ahead and try it out, and then you can go ahead and try B equals true. So then now we're adding the unit clause b equals true and check consistency again. If it's not consistent, you put a false. But if it's consistent, then you go and check C, right? And keep going. You can try to do that. And what you'll find out is that you're gonna terminate at false when you've put enough unit clauses that caused a contradiction. But this is actually expensive because you have to do quite a bit of consistency checks, right? And if you want to do consistency check, that is to see whether this is consistent with the knowledge base, you would run resolution. However, if you have already finished directed resolution, like we did here, and you used a variable ordering in this guy that correspond to what you want to do with the decision tree. So let me erase this part in a little bit. So in this case, I have A, B, C, D, E, and I use the reversed ordering here, A, B, C, D, E. So now let's see how this will facilitate the construction of the decision tree. So let me remove this guy here, and let's see what happens and how you can actually use this. So I'm going to start with A, and I'm going to first try to see whether A is true, right? So as we said, this last bucket represent the projection of the knowledge base on A. So this bucket actually contains everything that the knowledge base says about A. And it's already have the unity clause not A. So if I go ahead and set A to true, I'm going to get a clash here. And that immediately tells me that I false, that is inconsistent. I did not have to run resolution. I did not have to do basically any other consistency check. All I had to do is check the bucket for A, and I could already tell that this is inconsistent, that there will be no models in which A is true. And then I will go ahead and try now A equals false. So if I have A equals false, think of this as basically, setting the value of A equals to false. So what's going to happen to this clause? A equals false. This is going to go away. Let me make it a different color. This is going to go away. This is going to go away. This is going to go away. What else happens here? And this literal goes away. Okay, that's not what I have. And now I'm going to go ahead and try the variable B. And when I try the variable B, let me say I'm going to try B equals true, right? So now what do I have to do to check whether A false, B true is consistent? All I have to check is the last two buckets in this case. And at this point, with A false and B true, that is consistent with that, right? There is no conflicts. In fact, that tells me that both B could be true and B could be false. Both of these are actually consistent with what's going on. So let's pursue this guy here. Let's pursue the fact that B is actually true, and therefore simplify this further. What happens that when you have B equals true, what happens here is for this guy, this is going to go away, and this is going to go away. And that's basically the situation that I will have. So let's go and try C now. And I'm going to say C equals true, right? If I want to check what's going on here, if this is compatible, all I'm checking is these three buckets. The only thing that's in there is that C is false. So C being true will conflict with that. So I already know that I will have to put this guy here. And then I can go and instead try this and keep going. So the point here is that you can go and develop this tree and try the different branches. And as you are doing this, the consistency checks that you need to do can be done very efficiently on this guy. You don't have to run resolution or anything. It already has the information that you want, and that you can go this particular tree and develop it fully, where at each node, the only amount of work you have to do is basically linear in this guy. All right, so the tests that you have to do at every node to decide whether it's done or whether you're going to grow further below it, that amount of work is pretty easy. And the key here is to use variable ordering for bucket elimination, which is the opposite of what you have in your decision tree. Now, of course, there are better ways to construct decision trees for knowledge bases. In fact, later we're going to talk about decision graphs, which are even more efficient. That's a very famous representation of knowledge bases, ordered decision graphs, or what's known as ordered binary decision diagrams. We will study these in more details later, and we'll see they have many applications, but I just wanted to end it with this note on directed resolution. Okay, we said quite a bit about directed resolution. We gotta stop at this point and go into a new subject. So I'm gonna just take a look quickly here to see if there is any question. There is a question about what does characterizing a model mean? It means that if you have this decision tree and I want to ask you if something is a model or not, then you can tell pretty easily based on this decision tree. All right, this was an intense discussion on directed resolution. You'll see many more examples about all of this in your text. We will go now into the follow-up. So as I mentioned earlier, this was what was known as the DP algorithm, or the Davis-Putnam. It was originally proposed to do satisfiability. And part of the problem was the added clauses and the size grows. So then there was later an algorithm introduced by Davis, Putnam, Longman, and Loveland, which became known as the famous DPLL algorithm. And this had very modest space requirements and ended up being the basis of many things that happened later. We're going to start with it. You're going to see that it's conceptually very simple. But what we're going to do is do it in basically stages. So we're going to start with something that we're going to call SAT1, and then we're going to make it into SAT2, very minor modifications, and then we're going to get DPLL. All right. But DPLL is not what's happening with modern SAT solvers. There are more things that happened that eventually led to what we're going to call modern SAT solvers. Some people still tell you that modern SAT solvers are DPLL, but actually that's not technically correct. We're going to see that. So there's a couple of very interesting things that happened here that lead to modern SAT solvers, but that's going to be the evolution. And this is basically your chapter 3. Again, like chapter 2, there is more material than what we will actually cover. So you'll need to go by what's happening in the lecture as far as coverage. Okay, so SAT1 and SAT2, pretty straightforward. DPLL we add one more thing to get DPLL. So let's get on it and see what we're gonna finish by today. We're gonna use this very simple knowledge base, which is A implies B and simply B implies C. That's it. Okay, and 3 variables, 8 different variable instantiations. And if you look at these variable instantiations, I can represent them by something that looks like this. Now, this is starting to look like what we've just done. It's more like a decision tree if you want to think about it. But the point is, we're going to use it conceptually instead of constructing it. So let me put this here. Okay, so what you can see here is I have the variables A, B, C, and you can think of these as worlds. So each one of these is a variable instantiation, right? So this here is everything is true, This last guy, everything is false, and you have all of the other combinations. So the idea is that I'm going to try to search this tree, right? I'm not going to construct it explicitly, but I'm going to pretend I'm exploring this to find one of these guys that satisfy my formula. So I'm going to go and set, let's say we set A to true, and then we set B to true and C to true, and I will check this. Does this satisfy? Now, once all variables are known, checking satisfiability is easy, right? Because if you know that A is true, B is true, C is true, you can just plug them in here and evaluate the formula. So I can easily tell whether this is a satisfying assignment or not. If it is, I'm done. If it's not, I'm going to go back here and then try this guy here. And similarly, if this is a satisfying assignment, I'm done. Otherwise, I'm going to go up here and then go down here and try this guy. And I keep doing this. Now, if you have, we'll see the Zoto code for this quickly next. If you've done search before, if you've taken an Intro to AI course, what kind of search algorithm is this that's going to go like this? Go down here and then go this way, that way, and if not, it will go up all that way and go on. What is that? That's depth first search. It's called depth first search. And the main thing about depth first search, if you didn't know, and we write the code in just a little bit, it has very modest space requirements. So even though this tree itself is exponential, in particular, you have 2 to the n leaves there. Even though this is exponentially sized, depth first search can explore this while only using big O of n space. So because it doesn't need to really store the whole tree. It can only store enough information to keep track of the branches that it is exploring. So as far as space, this is excellent. And this was the motivation to go in this direction. Right. Now, there is the question, wait a minute, this can take exponential time, because what if this is the only guy that is a satisfying assignment? You have to explore all of these before you get to that. Right. But you'll see the significant advancements that have made to try to avoid this exponential complexity, on an average at least. Let's do this. What we will do is we will just write the code for this, and then we'll make 2 improvements for it, which was basically get us to DPLL. Let me write the first version of this. So this is SAT1, and it's going to take a knowledge base. It's going to take the number of variables, and it's going to take depth. So this is depth 0 here, and this is depth 1, and so on. Okay, let me write it quickly, and then you guys will see what's going on. So if D equals N, and delta equals this, return this. This will not only test satisfiability, it will also give you back a satisfying assignment if the knowledge base is satisfiable. Okay, and now you're going to see the value of the set notation that we talked about before. 3 more lines. Okay, that's basically it. So what's happening here is we have the knowledge base delta, and n is the number of variables. In this case would be 3. And d is the depth. Initially, we start by passing depth of 0. And it's very simple. You have these boundary cases where d equals n, and that means I've reached one of these leaves, right? So I've reached one of these leaves. And those are the first 2 guys here. Why is this not becoming red? So these are the 2 guys here where I've reached a leaf node, right? So the depth equals to n, right? So depth 0, 1, 2, 3. So this is depth 3. And in that case, what are the base cases? There are these. As I go down, right, I'm conditioning the knowledge base on the variable setting. So if I have A and I go down here, I'm going to condition the knowledge base on A being true. If I go down here, I condition further on B being false, and so on. So when I get to one of these leaves, I have already conditioned on every variable. So I've conditioned on A true, B true, C false. What happens when you condition on every variable? So if you have this particular knowledge base here, which is not A, B, and not B, C. When you condition on every variable, this thing will reduce to one of two things, right? Either true or false, exactly. When you condition on every variable, you either have true or false. This is the CNF, the closal form that represents true, and this is the one that represents false. Because every clause will either be subsumed, become true, or become the empty clause. So things will simplify to one of these two cases, and this is what's being tested here. So if I reach a leaf node and this guy is true, then I return an empty set of variables or literals. If it is false, I return fail. Now look, here's what's happening in terms of going down these two branches. I'm going to call sat1 by conditioning on this variable. We're assuming the variables are p1, p2, pn, okay? So I'm going to condition on this variable, same number of variables, I'm increasing the depth. If it did not fail, so I'm going down here and it did not fail, this is the variable setting that was returned by this guy. I'm going to take it and basically append to it the fact that I set P2 true. This is one branch. If I'm done, I'm done. If not, I get to this second branch. The second branch, I'm trying to condition now on the negation of that variable, and same story. If I tried both of them and both failed, then I return fail. So this is basically an implementation of depth first search. It's pretty bad in terms of complexity because you can do significantly better. We're going to see that, but that's the basic one that we're going to be working with. We'll make one simple change to it, which will make it into SAT2, and then we'll be very close to getting to the original DPLL algorithm. But stare at it again. Two base cases, and these are the recursive cases trying the two branches. And this guy will not only test SAT, it will either return fail if it's not satisfiable, and if it is satisfiable, it will give you back a variable instantiation. That is, if it goes down here and this ends up being satisfying, it would return this variable instantiation. It would return A true, B false, and C true. Okay, so you can make this way better by observing something very simple, which is that you really do not have to reach sometimes the leaves in order to end with success or failure. So if you look, for example, at this guy here, let me do this. If you look at this node here, this node represents A true, B false. So if you take delta and condition it on A and not B in this case, right? So I'm fixing A to true, I'm fixing B to false. What is it? Here's your delta. This is delta. What happens in this case? What happens when you condition delta on A true and B false? What do you get? Do it. Fix A to true and fix B to false. And someone already wrote this. So this is basically false. So I really, the minute I conditioned on A true and B false, I know I cannot find a solution, right? So I shouldn't go down here. I'm done. And here's another base case. So if you take, let's look at this guy here. Let's look at this node here. So if I condition on not A and not B, what do I get? So here, okay. What do I get? Here's the knowledge base and condition it on A false, B false. What happens? Okay, someone wrote this and that is true. What does that mean? What does that mean? That means if I set A to false and B to false, I know I have satisfied the formula. And I don't care about what the value of C is. Any value of C would actually work. So this is always a solution, and I could return at that point. So you can actually easily fix this by simply what? Can someone suggest a change to this code that will implement this idea by doing early checks for failure or success, where I don't really have to wait all the way until I reach a leaf node? I want to be able to return from these without having reached the bottom of the tree. It's actually a very, very simple change that we have to make here, and it will end up doing that. Right. So basically, someone is saying we just take this guy out, right? I know that when I reach a leaf, one of these will hit, but it's possible that even though I'm not at a leaf, that one of these guys will hit, and then that basically becomes SAT2 for us. Let me ask you another question. SAT1, the previous version, if it does not return fail, if it succeeds, it would return a full variable instantiation, right? Because it will succeed at one of the leaves, and therefore, if it succeeds at this leaf, it will return back A false, B true, C true. Okay. This new guy, SAT2, well, what would it return more generally when it does succeed? Is it guaranteed to always return a full variable instantiation? And someone saying no, it will give a partial variable instantiation back in general. Correct. So for example, if you happen to start by going down this branch and you hit this node, you're going to succeed here. You're going to say A false, B false, done. I figured it out. Then what this algorithm SAT2 would return will only return A false and B false. So it will be a partial variable instantiation. And the idea here is that you can complete it any way you want, and you're good. Okay, I just want you to set A to false, set B to false, and you're guaranteed to satisfy the formula. You can do with C whatever you want. Okay, now let's do one more concept, which will get us ready for the next step. And this is the notion of a termination tree. Termination tree gives you a sense of what happened when you ran this algorithm, how much work it actually did. I will mention it and show you a concrete example, and then you'll make an observation, and that should set the stage for DPLL, which in all likelihood we may just do next time. Let's look at this knowledge base. This guy has the following. A implies B, B implies not C, not C implies not D. And what we have here in terms of clausal form, what we have is not A, B, not B, not C, and then C, not D. Now, we run this algorithm, and I'm going to show you what we call the termination tree. The termination tree is the portion of that full tree that we saw that got explored. And it looks like this. You have this node. I tried A equals true, and then I tried B equals true, and then C, and then when I try C equals true, that was a conflict. I didn't get, and then I tried C equals false, and that was D. And then C equals true, that didn't work. And then I tried D equals false, and that worked. Now, what I'm going to show you next to this, each node, what was the state of the knowledge base in that case? So when we started, that was basically delta, right? That's the original guy. And then when I went and set A to true, what happened is, so we got this guy. Sorry, that would be not B and not C, and then finally C and not D. Okay, and then I went and set B further to true, and then the knowledge base simplified to the following. Okay, and then I went further and set C to true. What should I write here? What's the knowledge base here? This is after setting A to true, B to true, this is where the knowledge base is. And I went and I set C to true again. What do I get here? Someone is saying this, correct. So that is false. That's why I failed. And then I went and I tried this guy. Now, what is the knowledge base in this case? Which is you take this and set C to false. What happens here? It should be a simple knowledge base. Help me out here. And people are saying it's exactly the unit clause D. Very good. Now, then I went down here and I set D to true. What should I write here? Again, that's false. Okay. And finally, I went and I tried this. What should I write here? This is this guy true. This is when I got success. Okay. And this is where the guy finally returned. And when it returned the variable instantiation A true, B true, C false, the false. Okay. This is what is called a termination tree. It's an important concept because it is the actual work that was done by this algorithm. I want you to make an observation here. And this observation, when we integrate it in the code, we will get what people call DPLL. Could have it been possible for us to finish this work much earlier? Okay, so this is SAT2, right? SAT2 is doing depth first search. It went down this branch, and by the time it set C to true, said, "Oh, don't bother. A true, B true, C true is a losing variable instantiation. Nothing good can comes out of that." And then, then it went down here and went down here and then went down here. And it's like, okay, done. I figured out a solution. Here's the variable instantiation that satisfies the formula. There is something you learned earlier that can be integrated in this process that I claim should allow you to finish the search even after having set A to true. By the time you set A to true, you should say, done, I figured it out. I don't need to do anything. Think about it. What did we learn? A technique. I told you we will get back to it later, and even though I'll give you some more hints, even though it is not complete or even though it's not refutation complete, it's something that can be used. Aha! And now I get the answer called unit resolution from Sam. Good. Unit resolution, not just your resolution, unit resolution. Right. What happens if you apply unit resolution to this knowledge base here? Let's make this blue here. I set A to true, and that is my knowledge base, correct? What happens if we do unit resolution? You're going to resolve this with that. So what do I end up getting? I end up getting the clause not C, correct? Now, you can resolve this with that. What do you get? Not D. What's going on here? I started by saying, let's try A being true, correct? By simplifying the knowledge base, I got the conclusion, well, B must be true. And by doing unit resolution, I concluded C must be false and D must be false. So by taking the assumption that I've made, or the thing I'm trying, A being true, conditioning the knowledge base, and then running unit resolution, I concluded that in that case, if you've decided to set A to true, then you have to set B to true, C to false, and D to false in order to satisfy the formula. And I could have just ended here and I said, done. I fixed the value of every variable in a way that satisfies the formula. So the idea here is you take SAT2 and say, every time I set the value of a variable, every time I condition the knowledge base on a variable setting, I'm going to go run unit resolution. All right. And what happens in that case is either unit resolution will detect a contradiction and then you realize, oh, there's no point going down there. Or like what happened here, unit resolution will discover enough values of variables that will satisfy the formula. So it will allow you to detect failures or successes even earlier than what we've done. All right. Now, if we put that idea together, the code will look we can just do minimal changes to set2 because we want to set it up in a way to allow us to do even more cool things later. So I'm going to leave out the pseudo code for this version, which will end up being DPLL. So we wrote sat1 and then we wrote sat2, and the next version we're going to write, it's going to be DPLL, which is effectively sat2 plus unit resolution. And again, the reason we're not doing it now because we're going to rewrite the code in a different way to show you things that come up when you do that. So there's way more to the story than we just mentioned. But that's basically a good ending point here. So you can see now unit resolution, how often it's being invoked. It's being invoked effectively at every node in this search tree that's being explored by depth first search. And this explains why people have invested in it. And I made a remark last time, which may not have made much sense. Let me mention it again now. This is about how do you implement unit resolution in an efficient way so that not only do you do it, but you undo it. Because look what happens. If I'm going down here and then I set C to true and I did unit resolution and and then it didn't work. When I go up, I have to undo the setting of this guy and set something else. So I'm setting variables, running unit resolution, simplifying knowledge base, and then I'm undoing that. So it's not just doing, but it's the undoing that needs to be done efficiently. We'll have a chance to say something about this. Folks, conceptually, we got to DPLL today. We didn't write the code. We'll do it next time. And then you will see two further remarkable observations. Let me tell you about them briefly, which is this process that we did here is called chronological backtracking. So when you go down here and you set the value of this to true and it fails, you go and set it to false. And anytime you fail, you just go to the level up. And people discovered that could be a waste of time. Because when you fail here, it's possible that that has nothing to do with the fact that C was set to true. It may have been some earlier commitment you did above. So going and reversing C is a waste of time. So if you're able to figure out why did you really fail, you can actually jump to much earlier level and undo these things. That's one big idea. The other big idea is that sometimes unit resolution does not discover contradictions because it's not complete. But if certain clauses were added to the knowledge base, then it will empower unit resolution and then it will discover these things. So there is a very interesting way to do that. These are like some of the ideas that when you add to DPLL, you end up coming up to what people call modern SAT solvers today. And when we get to that last thing, which we will next time, you'll see it's like an orchestra of techniques playing together. All right, folks. So the last part of today's discussion, that's chapter 3, will be posted today, and you can start reading on that. But otherwise, we're done. Thank you, and I will see you next week.